Let's build a machine learning model together to predict FIFA 19 player rankings based on their in-game statistics. If I did my best to describe machine learning to you in just one sentence, I would call it a process where we feed the model raw data and it learns to find patterns and make predictions without us hard coding every rule, just like a human brain. And today we're using a random forest regression model, which grows many decision trees that repeatedly split players into smaller groups based on their in-game statistics. So now let's get coding and break this down. Our first step when building a machine learning model is always to import our libraries, which is the core tools we'll need to make our machine learning model work. We begin by importing NumPy to work with numbers and Pandas to work with the FIFA dataset. And finally, we import Matplotlib to help us make a pretty cool visualization later on. Our next step is to load the data. In this code snippet, our goal is to pull this dataset from Kaggle's file system into Jupyter and sanity check that it looks as expected. So we specify the CSV file and read it into Pandas data frame. Then we take a look at just the first few rows using the .head function to examine the dataset and how we might want to clean it. Now that we've made sure the data looks good and gotten familiar with some of the columns, it's time to choose our target and initial features. In this block of code, we decide what prediction task we're solving and strip away columns that we don't actually need. First, we designate the column called overall to be our target column, or Y. This is what the model will be learning to approximate as we train it. Then we assemble a list of columns to drop. This includes the target column itself, plus identifiers or any awkward fields. Finally, we construct X by dropping these columns from the overall dataset and Y by constructing the overall series. The net result that we end up with is X containing the candidate features that the model can learn from and Y containing the numeric ratings that the model is trying to predict. Now it's time to train and validate our data. When building a machine learning model, we always split our data into training data and testing data. In its training stages, we use that training data for the model to learn the features and recognize patterns within that dataset. During these stages, the testing data is top secret. Then, after the model has already been trained, we apply the testing data to see how well it performs on data that it's never seen before. Here we call a test size of 20%, leaving 80% for our training data, and a fixed random state, producing xtrain and ytrain for the training data, and xvalid and yvalid for evaluation. Next, let's identify our numeric and categorical features. In this block, our goal is to prepare for different pre-processing strategies that may come in the future based on the data type. So we look at xtrain and gather all of the columns whose data type is numeric into one list, and all of the columns whose data type is categorical into another. And for a quick sanity check, we print how many columns there are in each list. Next is the pre-processing pipeline. In this section, we write reusable recipes that describe how raw categorical and numeric features should be transformed and cleaned before they reach the model. And then we combine those recipes into a single object that can handle the entire data table in one shot. For numeric features, we define a pipeline that imputes missing values using the median of each column and standardizes the data. For categorical features, we first fill in missing categories with the mode of each column and then apply one-hot encoding. Finally, we wrap both of these pipelines in a column transformer, which is our preprocessor. This is configured to hit the entire dataset at once, applying the numeric pipeline to numeric features and the categorical pipeline to categorical features. And if you're curious about more ways to get your data ready for your machine learning model, you can check out a recent video I did all about data preprocessing. Next, let's build the full pipeline. Here our goal is to define the random forest regression model that we'll be using and chain it directly after the preprocessing so that training and prediction become one cohesive operation. Essentially, we first instantiate a random forest regressor, which has a specified number of trees, reproducible randomness, and built-in parallelism. And this gives us a flexible, nonlinear regression model that can handle mixed features. We then build another pipeline, this time with two steps, called preprocessor and model. Clearly, the preprocessor is the column transformer we built in the previous step, and the model is the random forest regressor. This means that any call to fit or predict on the random forest pipeline will first run the automatic imputing, scaling, and one-hot encoding, and then pass the transformed features into the random forest. Now it's time to run the training and validation. In this block, we finally let the model learn from the training subset, and even though this is just one tiny line of code, it really is the biggest part of the model. This is where we're fitting the pipeline on X and Y train. Then after it's done, we'll see how well it can make predictions for data it's never seen before. So we call predict on xValid. We're not providing the outputs or y values for the validation dataset because we want to see how well the model can figure those out on its own. We then compute mean absolute error on the values the model has predicted from the inputs of the validation dataset and the actual value. And this is the average absolute deviation between the predicted and the true values. Next, it's time to cross-validate our data. In this code snippet, we move from doing a train validation split just one time to a more statistically robust assessment. This function repeatedly splits the data into training and validation folds and fits the same pre-processing plus model pipeline on each training fold, then evaluating it on the validation fold. Once we're happy with the model's performance, we refit it on all the data. Here we've kind of forgotten about the training and validation datasets, and we're applying everything to the broader X and Y. Now we're in the final stages, and this feature extraction step will help us actually learn from the model. Here we'll code the part that helps us figure out what features are most important in predicting the player rankings in FIFA 19. Here we want to connect the random forest's internal scores back to the feature names. We put all the feature names in one list, line them up with the model's feature importances values, and store them in one data frame with feature and importance. And now that we have this data, our final step is to visualize it. We construct a horizontal bar plot where the y-axis lists all of the feature names and the x-axis shows their corresponding importance scores. After naming all of the axes and giving it a title, the result is a ranked visual summary of which numerical skills or categorical attributes the random forest considers most informative in predicting the player's overall rating. And it looks like the model decided that the most important feature was reactions. This is a numeric feature between 0 and 99 that shows how quickly a player responded to events in the game. And that is a robust, fully functioning random forest machine learning model for you. Make sure you send these FIFA 19 rankings to all of your friends, save this video for the next time you're working with ML, and follow for more.